So in this video, we are going to go over how to purify and isolate stereoisomers. We're also going to talk about Fischer projections, which are a different way to draw certain molecules. You might have seen Fischer projections in your biology class, but we'll talk about how to assign R and S to those projections. Okay, so let's start with how to purify and isolate stereoisomers. So remember, there are two different kinds of stereoisomers, diastereomers and enantiomers. Now, remember that diastereomers are not mirror images of each other, but they have the same connectivity. And then enantiomers are non-superimposable mirror images. So they are different in that sense. Now, with diastereomers, you have very different physical properties. So for instance, if you have cis and trans alkenes, they might have the same connectivity, but one is cis and one is trans, and they will have different physical properties like boiling point. So you could use distillation to separate. So you could separate your two diastereomers by their boiling point. You could also use something called chromatography. Now, chromatography is a way to separate polar molecules. So for instance, if one molecule is more polar than another, you can take advantage of its polarity and run it through some sort of medium that is also polar. So then the polar compounds are going to stick to the polar medium, and the less polar compounds will just keep moving through that medium. So you could separate something that way. The other way that you could separate diastereomers is by using recrystallization. And you can read about recrystallization in your Zubrick manual. But with recrystallization, you can separate molecules by their solubility. So let's say you have two diastereomers with different levels of solubility in a particular solvent, like water. You could use that to separate them. Or if something's more soluble than something else in water, you could recrystallize, and that will remove or separate one of the diastereomers. Now, enantiomers are a little bit more difficult to separate. In fact, they're very difficult to separate. So the reason for that is they have the same physical properties. So I'll use blue here so that we don't get them mixed up with our diastereomers up above. Now, because enantiomers have the same physical properties, there's not a lot of options here for separating them. However, remember that enantiomers are mirror images of each other that are non-superimposable. So you could assign R to one enantiomer and S to another enantiomer, for example. So that is one difference that they have. In order to separate R and S enantiomers, you could crystallize them. So you could perform crystallization and then separate the two different crystals using tweezers and a microscope. So a scientist named Louis Pasteur, he did that with tartaric acid. He saw that there were two different types of crystals. They did look different, so he separated them just by using his sight through a microscope and a pair of tweezers. So really you're separating mirror images. Oops, let's see, let me erase that parentheses there. Now that is painful and takes a long time, so there is another way that you can separate enantiomers. So let me show you on the next slide. So another way to separate enantiomers is to use what are called chiral resolving agents. So what we could do, for example, let's say we have this molecule. So this is an amine, and let's draw its enantiomer. So again, we could either crystallize these and then use a microscope and some tweezers to separate all of the different crystals, or we could react these two with something called S-maleic acid. Oops, that looks like an E. That should be a C. Okay, so what ends up happening is the nitrogen on both of these molecules is going to attack an acidic hydrogen on maleic acid. So maleic acid, or S-maleic acid, looks like this. Notice that there is a stereocenter there, and that is the S stereocenter. So again, nitrogen will come in and grab onto the most acidic hydrogen. That will leave behind a lone pair of electrons on oxygen, and we end up with a salt. So that's our first salt. And then our other salt, let's use a different color. We'll use red. Our other salt will do a similar thing, but we'll just end up with, of course, a different stereocenter for our NH3 here. Okay, so this is our, or these are our two salts that we would end up with. Now, notice that the stereocenter underneath the nitrogen on both of these salts, those are different. So we have let's see this. So this is an S enantiomer. This is an R enantiomer down below. But the other half of the salt stays the same. So we have S and S. So the salt up above is SS and the salt down below is RS. So they are diastereomers. All right, so we end up with salts that are diastereomers. And remember, diastereomers have different physical properties. So now we can go back to our different methods for separation for diastereomers. And now we can separate those compounds using distillation or chromatography or recrystallization, whatever would work best to separate them. Now, at the very end, once they're separated, we would need to turn them back into their original molecules. So we would probably add, some sort of other reagent that would reverse the effects of what we did before. So this is something that scientists do a lot. They have to separate these enantiomers using chiral resolving agents. And remember at the very beginning of chapter 5 when we were discussing isomers, specifically enantiomers, we said that it's really important to know the difference because sometimes one enantiomer will kill you and another enantiomer will save your life. So you do need to separate them quite often. And this is how you can do that. Okay, so let's wrap up chapter 5, and we're going to discuss one last way to draw molecules, at least for now. We'll talk about other ways later. So we're going to go over Fischer projections. So this is one way that we can draw stereocenters, and this is kind of a shortcut for drawing stereocenters. So in a Fischer projection, we have something that might look like this, for instance. Just looks like two lines crossing each other with different substituents attached, and your stereocenter is in the middle. So that is some sort of carbon there, let's say. Now, in a Fischer projection, we can say that all horizontal lines are wedges, and all vertical lines are dashes. So let's draw our example below so that all of the horizontal lines are wedges and all of the vertical lines are dashes. All right, so I'm going to draw a little bow tie in the middle and color it in. And then I'll draw some dashes going up and down. And then I'll just write in all of my different groups. Now again, ET stands for ethyl, and ME stands for methyl, just in case you hadn't seen those. Okay, so now what we're going to do is prioritize each of these different groups that are attached to the stereocenter in the middle. So let's see, what would have first priority? The methyl group the OH group, the ethyl group, or the hydrogen? So remember, ethyl is CH2CH3, methyl is just CH3, if that helps you figure out which would have higher priority. So the highest priority group would be OH because oxygen is heavier than carbon. Now we have to decide between methyl and ethyl and hydrogen. So methyl and ethyl have carbons directly attached to the stereocenter. Those are heavier than hydrogen, so we know hydrogen is priority 4. That's typically our lowest priority atom. So now we have to decide between ethyl and methyl. So would this carbon have higher priority, or would this carbon have higher priority? So the ethyl carbon would have higher priority because it's bonded to 2 hydrogens and a carbon, whereas the carbon in the methyl group is only bonded to 3 hydrogens, and those are all really low in atomic mass. All right, so ethyl gets priority 2, methyl gets priority 3. So now let's draw a circle going from 1 to 2 to 3. And is that going in a clockwise direction or in a counterclockwise direction? So that is going in a clockwise direction. So normally we would assign this as an R configuration, but our lowest priority atom is pointing out towards us. So we actually have to flip our configuration assignment. So it's actually an S configuration. All right. So again, this is just a shortcut for drawing stereocenters, and this is going to come up again in the future, especially when we start talking about carbohydrate chemistry. So in the future, we'll talk about sugars, for instance, which is one type of carbohydrate, and we'll need to draw structures like this one. So as an example, let's look at another molecule. So let's look at this one. And this has more stereocenters than the last one. So this molecule actually has 2 stereocenters. So these carbons in the middle are attached to 4 different groups. Okay, now remember, all of the horizontal lines will be wedges, and all of the vertical lines will be dashes. So let's redraw this molecule, and then we'll assign R and S to those stereocenters. Now, I tend to just draw a straight line down the middle, and then I'll draw a dash at the very bottom and the very top. So one way you can think about this, and the professor who normally teaches organic chemistry, he kind of introduced me to this idea, but he calls this the cat tummy view. So if you have a cat at home, do they ever kind of roll over onto their back and put their paws up. I know my dog does it sometimes, but you can think of it as, their paws are pointing out towards you. So maybe there's a little paw right here and a little paw over here. Then there's their tummy. And then they've got their back paws pointing out towards you as well. And then they've got their tail down below, and then their head up above. So you can think of it like a cat. Oops. I hit the the next slide. I didn't mean to go dark on you there. Okay, so if you like to kind of think about this three-dimensionally, imagine a cat laying on its back, its paws are reaching up towards you, and then its head and its tail are pointing away from you. All right, so anyway, going back to our Fischer projection up above, let's assign R and S to the stereocenters. So let's start with the one at the top. So that carbon is bonded to a bromine, an oxygen, a carbon down below, and a hydrogen. So what would get highest priority? Bromine, oxygen, carbon, or hydrogen? Bromine. Bromine is the heaviest atom that stereocenter is bonded to. What would come next? Oxygen, carbon, or hydrogen? Oxygen. And then what comes next? Carbon or hydrogen? Carbon. And then hydrogen is our lowest priority. So let's draw a circle going from 1 to 2 to 3. I'll just draw it off to the side to make it easier to see. So is that pointing or turning in a clockwise direction or a counterclockwise direction? Counterclockwise. So counterclockwise is associated with S. However, hydrogen is pointing out towards us. So this would actually be R. So this indicates S, but it's not S because of the hydrogen pointing out towards us. All right, now let's look at our other stereocenter down below. So that is bonded to a chlorine, an oxygen, a carbon up above, and a hydrogen. So what would have highest priority? Chlorine, oxygen, carbon, or hydrogen? Chlorine. And then what comes next? Oxygen, carbon, or hydrogen? Oxygen comes next, and then carbon, and then we have hydrogen. Okay, so now let's draw a circle going from 1 to 2 to 3. So is that going in a clockwise direction or a counterclockwise direction? Counterclockwise, so we would assume that this is an S configuration, except hydrogen is pointing out towards us. So this is also an R configuration. So remember, if that lowest priority atom is pointing out towards you, then you flip your assignment from what you would expect. Okay, so that's it for chapter 5. And again, Fischer projections are going to come up in the future. So I wanted to introduce them here since it has to do with geometry and R and S configurations. All right, so we are done with chapter 5. I will see you next week when we start chapter 6. And please let me know if you have any questions.